Welcome to the deep dive. Ever find yourself looking at a really complex topic and just wishing someone could, hand you the essentials, the absolute core insights, maybe with a few aha moments to make it all click? Well, that's pretty much what we're here to do for you today. We are setting out on a comprehensive deep dive into fundamental chemistry. We've got a whole range of concepts lined up, from the tiniest particles making up everything around us to the huge reactions shaping our world. Think of this as your roadmap to the core ideas about matter and energy.
Yeah, and what's really remarkable about chemistry is how it all connects. These aren't just like separate facts floating around. They really build on each other. We'll dig into not just what these concepts are, but crucially, why they matter and, how our understanding has actually changed over time. Get ready to connect some pretty cool dots.
All right, let's jump right in. Our journey into chemistry, it really has to start with the atom, the absolute foundation. It's kind of wild how our ideas about this basic building block have evolved. We should probably start with John Dalton and his billiard ball model. Back in his day, early 1800s, this was totally revolutionary stuff. He basically said, all atoms are indivisible and indestructible. Atoms of one element are identical. Compounds are just combinations of elements. And chemical reactions are rearrangements. 4 big points.
Absolutely. A brilliant starting point, really paved the way.
Yeah.
But, as science got better tools, a couple of those foundational points started to, not hold up completely. Like you said, atoms being indivisible.
Yeah.
How did that idea get disproven?
Oh, yeah, that one's pretty obvious now. We know atoms are definitely divisible. I mean, protons, neutrons, electrons, they're inside the atom.
Yeah.
So much for the solid billiard ball, huh?
Exactly. And not just that one. He also thought all atoms of the same element were identical. But then we discovered isotopes.
Right, isotopes. Same element, so same number of protons, but a different number of neutrons, so slightly different masses.
Precisely. So 2 of his original key ideas needed a big update.
So the atom isn't just this simple solid ball. And this is where it gets really interesting. J.J. Thomson comes along with his plum pudding model.
Yeah.
He's the one who discovered the electron, right? Using those cathode ray tubes. He pictured them like little negative plums stuck in a positive pudding.
A crucial step to include subatomic particles. But the real game changer, the one that shattered the plum pudding idea, was Ernest Rutherford's gold foil experiment. He shot these tiny positive things, alpha particles, at super thin gold foil. And what happened next was just, wow.
Most went straight through.
Most sailed right through, which told him the atom is mostly empty space. But, and this is the key, a very small number bounced back or deflected sharply, like they hit something small, dense, and positive right in the middle.
And that was the nucleus, the tiny, dense, positive core. So Rutherford gives us the nuclear model, mostly empty space, tiny, heavy nucleus.
Exactly. From there, we sort of jump to the Bohr model. People often call it the planetary model.
Yeah, with electrons orbiting like planets around the sun. It helped explain why atoms give off specific colors of light.
It was a useful visual, for sure, but still not the whole story. The really mind-bending part came with the wave mechanical model.
Ah, the wave mechanical model. So electrons aren't on fixed paths anymore. What's the picture now?
It's a huge leap. Instead of fixed orbits, think of electrons existing in regions of probability. We call them orbitals or electron clouds. It's less about knowing exactly where an electron is and more about mapping where it's most likely to be found, kind of like a fuzzy cloud.
Okay, that makes more sense. So inside this cloud, near the nucleus, what are the actual subatomic particles? Can you break those down?
Sure. The key players are protons. They've got a positive charge, +1, mass of 1 AMU, that's atomic mass unit, and they live inside the nucleus. Then neutrons, no charge, so 0. Also mass 1 AMU, and they're also in the nucleus with the protons. And finally, electrons. They have a negative charge, -1. Their mass is tiny, basically negligible, so we say 0 AMU, and they're the ones outside the nucleus in those orbitals.
And that balance of charge is crucial, isn't it? Atoms are normally neutral.
That's right, because in a neutral atom, the number of positive protons must equal the number of negative electrons. Their charges cancel out perfectly.
And then back to isotopes, like you mentioned, let's take chlorine-35 as an example. What do those numbers mean?
Okay, so for chlorine, the atomic number is always 17. That's the number of protons, defines it as chlorine. The 35 is the mass number, which is protons plus neutrons. So chlorine-35 has 17 protons and 35 minus 17, 18 neutrons. Other chlorine isotopes might have different numbers of neutrons, like chlorine-37.
And understanding isotopes is key for calculating the atomic mass on the periodic table, because that's an average.
Exactly. It's a weighted average based on how abundant each isotope is naturally. So if you had, say, element Q, 77% at 83.7 AMO, and 23% at 89.3 mu, you'd calculate the weighted average. Comes out to 84.99 mu.
So thinking about those electrons again in their clouds, does their energy change depending on how far they are from the nucleus?
Absolutely.
Yeah.
The further an electron is from the nucleus, the higher its energy level. Think of it like climbing stairs away from the nucleus. Each step up is a higher potential energy level, or PL.
Higher PL number means more energy and greater distance.
Got it. Which brings us to electron configurations. We talk about ground state and excited state.
Right. The ground state is the electron's normal lowest energy arrangement. For calcium, that's 2-8-8-2, 2 electrons in the first shell, 8 in the second, and so on. An excited state happens when an electron absorbs energy and jumps to a higher energy level than it normally would be in. So calcium might temporarily become 2-8-7-3. One electron jumped further out.
And when that electron falls back down from the excited state, that's when we see light, the bright line spectrum. Precisely. When an electron drops from a higher energy level back to a lower one, it releases that extra energy as a specific packet of light, a photon. Since every element has a unique electron configuration, each element emits a unique pattern of light colors, its own bright line spectrum. It's like a fingerprint for identifying elements.
Okay, last concept for this part, valence electrons. These seem super important.
Oh, they are the most important electrons for chemical reactions. Valence electrons are simply the electrons in the outermost energy shell of an atom. They determine pretty much all of an element's chemical properties, how it bonds, how reactive it is. Like rubidium, it has just one valence electron way out there. It's very eager to lose it, making it highly reactive.
Okay, so we've zoomed in on the atom. Now let's zoom back out to matter itself. How do chemists even start classifying all the different stuff in the world?
It starts with a basic division. Homogeneous versus heterogeneous. Homogeneous means it looks the same throughout. Uniform composition, particles evenly mixed. Think salt water or pure air. Heterogeneous means it's not uniform. You can see different parts, uneven distribution, like sand in water or chocolate chip cookie dough.
And within those, we also distinguish between pure substances and mixtures. What's the key difference there?
A pure substance has a fixed composition and definite properties. It's either an element, the simplest form, like iron, Fe, or a compound where two or more elements are chemically bonded in a fixed ratio, like salt, NaCl, or carbon dioxide, CO2. A mixture, on the other hand, is just a physical blend of substances. The components keep their own identities and can be mixed in various proportions. Air is a mixture of gases. Salt water is salt mixed in water.
And there's a law about that fixed ratio in compounds, right? The law of definite proportions.
Yes, that's fundamental. It states that a specific chemical compound always contains the same elements combined in the same fixed proportion by mass. Water is always H2O, 2 hydrogens to 1 oxygen by atom count, which means a fixed mass ratio too. That's what makes it different from just mixing hydrogen and oxygen gas.
Now let's get into the language chemists use formulas and equations. There are those special diatomic elements first.
Ah, yes, the diatomics. 7 elements that naturally exist as 2 atom molecules when they're pure and uncombined. They always travel in pairs.
I remember the mnemonic BRIN-NCl-HF for them. Broman, iodine, nitrogen, chlorine, hydrogen, oxygen, fluorine.
That's the one. Br2, I2, N2, Cl2, H2O2, F2. Very handy to remember.
And then there are different types of formulas, empirical versus molecular.
Right. An empirical formula shows the simplest whole number ratio of atoms in a compound. Like for glucose, C6H12O6, the simplest ratio is CH2O. That's the empirical formula. The molecular formula shows the actual number of atoms of each element in one molecule. So for glucose, that's the full C6H12O6. You can figure out the molecular formula if you know the empirical formula and the compound's total molar mass.
Okay. Now, another basic particle question.
Right.
Atom versus ion. What makes an ion different?
Good question. They're related but distinct. An atom is neutral protons equal electrons. An ion is an atom, or even a group of atoms, that has gained or lost electrons, so it has an overall positive or negative charge. Protons and electrons are not equal. And we also have polyatomic ions. Those are groups of atoms covalently bonded together that act as a single unit with a charge. Like the phosphate ion, PO4, which has a 3 charge found in things like calcium phosphate, C3PO42.
Got it. So reading formulas like, say, 5LL2CO33. What are all the numbers telling us?
Okay, the subscripts, the little numbers within the formula unit, tell you how many atoms of that element are there. In Al2CO33, there are 2 aluminum atoms. The 3 outside the parenthesis means you multiply everything inside by 3, so 3 carbon atoms, and 3 times 3, which is 9 oxygen atoms. Now, the big number out front, the coefficient, the 5 front in your example, tells you how many whole units you have. So in 5Al2CO33, you'd multiply everything by 5. 10 Al atoms, 15 C atoms, and 45 O atoms total. For hydrated compounds, the number before the H2O just shows moles of water attached.
And why do compounds always end up neutral overall when they form?
Because the total positive charge from the positive ions must exactly balance the total negative charge from the negative ions. The sum of the oxidation numbers, or charges, has to add up to 0. So if lithium Li+ combines with phosphate PO43, you need 3 Li+ ions for every 1 phosphate ion to balance the charges, forming Li3PO4.
And those Roman numerals and names, like iron 3 hydroxide.
Crucial. They indicate the specific charge of the metal ion in that compound. Many metals, especially transition metals, can form ions with different charges. Iron can be +2 or +3, so iron 3 tells you explicitly that in this compound, iron has a +3 charge. Without it, you wouldn't know which iron ion it was.
Okay, so now we have atoms, compounds. Let's talk chemical reactions. Reactants turn into products.
So that's the core idea. You start with reactants, the substances you begin with, and they undergo a chemical change to form products, the new substances. In CH4 plus 3O2, NO2 plus 2H2O, methane and oxygen are reactants, CO2 and water are products. Atoms just get rearranged.
And energy is involved, endothermic versus exothermic.
Key distinction. Endothermic reactions absorb energy from their surroundings. Energy is essentially a reactant. Think of melting ice it needs to take in heat. Exothermic reactions release energy.
Yep.
Energy is a product. Burning fuel releases heat. If you see energy like plus 146.3 kiloj on the product side, it's exothermic.
Which ties directly into a fundamental law,
Right.
the law of conservation of mass. What does that mean for reactions?
It's absolutely fundamental. It means matter, or mass, cannot be created or destroyed in a chemical reaction. The total mass of the reactants must equal the total mass of the products. This is why we must balance chemical equations, ensuring the same number and type of atoms are on both sides. It makes chemistry quantitative and predictable. You can even figure out a missing reactant or product if you know the others and apply the law.
And chemists classify reactions into different types, right?
Yep. 4 main types help organize things. Synthesis is combining things, A plus B, A, B. Decomposition is breaking something down, A, B, A plus B. Single replacement is one element kicking another out of a compound, A plus B, C, A, C plus B. And double replacement is when ions in 2 compounds swap partners, AB plus CDS, AD plus CB. We even have reference tables, like an activity series, Table J, to predict if a single replacement will actually happen, and solubility rules, Table F, to see if products in a double replacement will form a solid precipitate or stay dissolved.
Okay, chemistry isn't just about what, it's also about how much. This is where the math and the concept of the mole becomes really central.
The mole. It's not the furry kind. It's the chemist's counting unit for atoms and molecules because they're so incredibly tiny. 1 mole is 6.02 by 1023 particles. That huge number is Avogadro's number. It's like a supersized dozen. It lets us connect the mass of something we can weigh in grams to the actual number of atoms or molecules involved. It's the bridge between the micro and macro worlds.
And that leads to gram formula mass or molar mass. How's that used?
The gram formula mass, GFM, or molar mass, is simply the mass in grams of exactly 1 mole of a substance. You calculate it by adding up the atomic masses from the periodic table for all atoms in the formula. We use it constantly for calculations, like finding the percent composition of an element in a compound, say the percentage of magnesium in magnesium nitrate, MgNO32, or even figuring out the percentage of water in a hydrated crystal.
So we've got particles, moles, masses. What about the states of matter? Solid, liquid, gas? What's the fundamental difference?
It all comes down to particle energy in motion and the forces between particles. Solids. Particles are tightly packed, strong attractive forces. They mostly just vibrate in fixed positions, definite shape, definite volume. Liquids. Particles have enough energy to slide past each other. Forces are weaker than solids, but still significant. Definite volume, but take the shape of the container. Gases. Particles are far apart, moving randomly and rapidly, very weak forces between them. They fill whatever container they're in. Indefinite shape, indefinite volume.
And changing between these states always involves energy changes. Which ones absorb energy, which release it?
Think about what requires heating up. Melting, solid to liquid, vaporization or boiling, liquid
Yeah.
to gas, and sublimation, solid directly to gas. Those are all endothermic. They absorb energy. And the ones that happen when things cool down, freezing, liquid to solid, condensation, gas to liquid, and deposition, gas directly to solid, those are exothermic. They release energy.
We often see heating and cooling curves to show this. What do the different parts of those curves represent?
Those curves are great. The sloped sections, where temperature is changing, show changes in kinetic energy. The particles are speeding up or slowing down. The flat sections, the plateaus, are where phase changes happen. Temperature stays constant because the energy being added or removed is changing the potential energy it's being used to overcome intermolecular forces, like during melting or boiling, or allowing forces to take hold, like during freezing or condensation. Kinetic energy doesn't change during a phase change.
So temperature itself, what is it really measuring?
Temperature is basically a measure of the average kinetic energy of the particles in a substance. It tells us how hot or cold something is and determines the direction of heat flow, always hot to cold. And a key point for calculations, especially with gases, always use Kelvin. Convert Celsius to Kelvin, C plus 273, for gas law problems, like using the combined gas law to find gas volume under new conditions.
Speaking of gases, we often use the ideal gas model based on the kinetic molecular theory, KMT. What are the main ideas of KMT?
KMT gives us a picture of a perfect or ideal gas. Key ideas are, gas particles themselves have negligible volume compared to the space between them. They move in constant random straight-line motion. All collisions are perfectly lead. Elastic energy is transferred, not lost. And, crucially, there are no significant attractive or repulsive forces between the particles.
Okay, so no real gas is perfectly ideal. When do real gases behave most like this ideal model?
Real gases act most ideally under conditions of low pressure and high temperature. High temperature means particles move fast, overcoming any weak attractions. Low pressure means they're far apart, minimizing interactions. The gases that behave most ideally most often are hydrogen, H2, and helium, because they're very small and have the weakest intermolecular forces. And related to this is Avogadro's hypothesis. Equal volumes of any gases at the same temperature and pressure contain the same number of particles.
Lastly, for this part, how do we actually separate different kinds of matter if they're mixed together?
We use various techniques based on differences in physical properties. Filtration separates an insoluble solid from a liquid, using filter paper like sand, from water. Distillation separates liquids with different boiling points. You boil the mixture, the substance with the lower boiling point turns to vapor first, then you condense it separately. Good for separating ethanol and water, or components of crude oil. And chromatography separates substances based on how they interact differently with a stationary phase, like paper, and a mobile phase, like a solvent. Think separating the colors in ink.
All right, let's shift to maybe the most powerful tool in chemistry, the periodic table. It's so much more than just a chart on the wall.
Oh, absolutely. It's an incredibly organized map of the elements.
Yeah.
The way it's arranged tells you so much. Elements in the same horizontal row, a period, all have the same number of electron shells. Third period elements all have 3 shells. And elements in the same vertical column, a group, have similar chemical properties because they have the same number of valence electrons. Group 16 elements all have 6 valence electrons, so they tend to react similarly.
And you can easily spot the different types. Metals, nonmetals, metalloids.
Yeah, the table makes it clear. Metals are generally on the left side of that staircase line, except hydrogen. Nonmetals are on the right. And the metalloids, those elements with properties of both, like silicon and germanium, they border that staircase. B, E, Z, G, S, B, T, T, at.
So what are the typical properties we associate with metals versus nonmetals?
Metals are generally malleable, can be hammered flat, lustrous, shiny, ductile, drawn into wires, and good conductors of heat and electricity. Nonmetals tend to be the opposite. Poor conductors, brittle if solid, often dull-looking. And this connects to ion formation. How does losing or gaining electrons affect the size of the atom?
Okay, if a metal loses electrons to become a positive ion, it gets smaller, right? Because it might lose its whole outer shell.
Exactly.
And if a nonmetal gains electrons to become a negative ion, it gets bigger because there's more electron repulsion.
You got it. Metals lose electrons, form positive ions, become smaller. Nonmetals gain electrons, form negative ions, become larger.
So what about the noble gases over in group 18? Why are they called noble?
They're called noble because they're chemically standoffish, very unreactive. They generally don't form compounds with other elements.
Because they already have that full outer shell of electrons, the stable octet.
Precisely. They have 8 valence electrons, except helium, which has a full first shell with 2, making them incredibly stable. They have no need to gain, lose, or share electrons. They're happy as they are.
And some elements can exist in different forms, like oxygen and ozone, or diamond and graphite, allotropes.
Yes, allotropes, same element, but the atoms are bonded or arranged differently in space. This different structure leads to different physical and chemical properties. Carbon, as soft graphite versus hard diamonds, is the classic example.
Okay, let's talk trends on the table. As you go down a group, what happens to atomic radius, ionization energy, and electronegativity?
All right, going down a group. Atomic radius increases. You're adding more electron shells, more layers, so the atoms get bigger. There's also more shielding of the outer electrons from the nucleus. Ionization energy. The energy needed to remove the outermost electron decreases. That outer electron is further away and shielded, so it's easier to remove. Electronegativity, the atom's attraction for electrons in a bond, also decreases. The nucleus has less pull on distant electrons.
And what about going across a period from left to right?
Going across a period, atomic radius decreases. You're adding protons to the nucleus, increasing the positive charge, which pulls the existing electron shells in tighter. No new shells are added. Ionization energy increases. Electrons are held more tightly by the stronger nucleus, so it takes more energy to remove one. Electronegativity increases. The stronger nuclear charge means the atom attracts bonding electrons more strongly.
Okay, now for the glue holding atoms together, chemical bonds. And a key point. Forming bonds releases energy, breaking bonds requires energy.
That's a fundamental energy principle in chemistry. Bond formation is stabilizing, releases energy. Bond breaking requires energy input.
How do we visualize these bonds, especially the valence electrons involved? Lewis dot diagrams.
Lewis dots are great for that. They just show the valence electrons around the element's symbol. Carbon has 4 dots. We can draw them for single atoms. For ions, showing the gain or loss of electrons, like O2 or Mg2+. And for molecules, showing shared electrons, like H2O or CO2. And based on how electrons are handled, there are 3 main types of bonds.
Right. Metallic, covalent, and ionic. What's the story with each?
Okay, metallic bonds are found in metals. The key idea is a sea of mobile electrons. Metal atoms donate their valence electrons to the shared sea that flows around the positive metal ions. This mobility explains conductivity and malleability. Covalent bonds form when nonmetals share electrons, usually to get a stable octet. A single bond shares 2 electrons, double shares 4, triple shares 6. It's a cooperative arrangement. Ionic bonds form between a metal and a nonmetal through the transfer of electrons. The metal loses electrons, becomes a positive ion, education. The nonmetal gains electrons, becomes a negative ion. The strong attraction between these opposite charges is the ionic bond.
And within covalent bonds, we can have polar or nonpolar sharing. What determines that?
It comes down to electronegativity difference. If 2 nonmetals have a significant difference in electronegativity, they share electrons unequally. The electrons spend more time near the more electronegative atom, creating partial charges. That's a polar covalent bond, like in water, HO. If the electronegativity difference is very small, or 0, like between 2 identical atoms, ClCl, they share electrons equally. That's a nonpolar covalent bond.
And this idea of polarity extends to the whole molecule. I remember SNP.
SNP is a great mnemonic. Symmetrical nonpolar, asymmetrical polar. Even if a molecule has polar bonds, if its overall shape is symmetrical, the polarities can cancel out, making the molecule nonpolar, like CO2, which is linear. If the molecule's shape is asymmetrical, the polarities don't cancel, and the molecule has an overall dipole, making it polar, like water H2O, which is bent.
So, practically speaking, how do these bond types affect a substance's properties, like melting point, conductivity?
Big time, generally. Metallic substances. Moderate to high melting boiling points. Malleable, conductive, solid, liquid, or aqueous. Covalent molecular compounds. Low melting boiling points, often soft or brittle, usually non-conductive in any state. Ionic compounds. High melting boiling points, hard but brittle, non-conductive as solids, but conductive when melted or dissolved in water. Aqueous, because the ions become mobile.
Okay, beyond the bonds inside molecules, there are also forces between molecules, intermolecular forces, or IMFs.
Yes, IMFs. These are the weaker attractions between separate molecules. They include things like London dispersion forces, present in all molecules, dipole forces between polar molecules, and the special stronger case of hydrogen bonding. What's fascinating is that the physical state of a substance at room temperature is largely determined by the strength of its IMFs. Iodine, I2, is solid because it has relatively strong dispersion forces, while fluorine, F2, which is much smaller, has weaker forces and is a gas.
And this affects boiling points too. Stronger IMFs mean higher boiling points.
Exactly. It takes more energy, higher temperature to overcome stronger intermolecular attractions and turn a liquid into a gas. Compare ammonia, NH3, which has hydrogen bonding and boils at negative 33 degrees C, with methane, CH4, which only has weak dispersion forces and boils way down at mega 161 degrees C. The stronger IMFs in ammonia mean a much higher boiling point.
All right, let's move into solutions. A lot of chemistry happens when things are dissolved. How do we know what dissolves in what?
The golden rule is like dissolves like. Polar solids dissolve well in polar solvents, like water. Nonpolar solutes dissolve well in nonpolar solvents like oil or hexane. So something polar like ammonia, Na3, is very soluble in polar water, while nonpolar methane, CH4, is barely soluble in water at all.
And how do temperature and pressure play a role in solubility?
For solids dissolving in liquids, usually increasing the temperature increases solubility and can dissolve more sugar in hot water than cold. But for gases dissolving in liquids, it's the opposite. Increasing the temperature decreases solubility. Warm soda goes flat faster. And for gases, increasing the pressure increases solubility. That's how carbonation works.
We use solubility curves, like on table G, to figure this out quantitatively.
Yes, those curves are really useful. They show the maximum amount of solute that can dissolve in a given amount of solvent, usually 100 grams of water, at different temperatures to form a saturated solution. You can use the curve to see if a solution is unsaturated, below the line, saturated on the line, or supersaturated, above the line, unstable. You can even calculate how much solute precipitates out if you cool a saturated solution.
So when we have a solution, how do we describe its concentration? Molarity %.
There are several ways. Molarity M is very common in chemistry. Moles of solute per liter of solution. Percent by mass is mass of solute divided by total mass of solution times 100. Percent by volume is similar, but uses volumes. And for very dilute solutions, we often use parts per million, ppm.
Now, something interesting happens when you dissolve something non-volatile, like salt, in water. It affects boiling and freezing points.
Yes, these are colligative properties. Adding a non-volatile solute to a solvent actually raises the boiling point and lowers the freezing point of the solvent. And the more solute particles you add, the greater the effect. This is key. Ionic compounds like salt, NaCl, break apart into ions, Net plus and Cl, in water, so they produce more particles per mole than a molecular compound like sugar, which stays as whole molecules. That's why salt has a bigger impact on freezing boiling points than sugar does.
What about vapor pressure? How does that relate to solutions and boiling?
Vapor pressure is the pressure exerted by the gas molecules that have escaped from the surface of a liquid in a closed container. Boiling occurs when the vapor pressure of the liquid equals the surrounding atmospheric pressure. As the temperature of a liquid increases, its vapor pressure increases because more molecules have enough energy to escape. And if a substance has stronger intermolecular forces, its vapor pressure will be lower at a given temperature because the molecules are held more tightly in the liquid phase.
Let's switch gears to kinetics. How fast do reactions actually happen? What's needed for a reaction to occur at all?
For a reaction to happen, reactant particles must have an effective collision. That means two things. They need to collide with enough energy, called the activation energy, to break old bonds and start forming new ones. And they need to collide with the correct orientation or alignment so the right parts of the molecules hit each other. Not just any collision works.
So what factors can we change to speed up or slow down the rate of reaction?
Several factors influence reaction rate. Temperature. Higher temperature means faster particles, more frequent, and more energetic collisions, so the rate increases. Surface area. Increasing the surface area of solid reactants exposes more particles to collision, so the rate increases. Think powder reacting faster than a solid chunk. Concentration. Higher concentration of reactants means more particles packed into the same space, leading to more frequent collisions, so the rate increases. And of course, catalysts.
Right, catalysts, they speed things up without getting used up themselves. How do they do that?
Catalysts provide an alternative reaction pathway, a different mechanism that has a lower activation energy. They make it easier for the reaction to happen, so it goes faster, but they don't change the overall reactants or products, and they're regenerated at the end.
We can see this on potential energy diagrams, right? Those graphs showing energy changes during a reaction.
Exactly. Those diagrams map the potential energy from reactants to products. You see the initial energy of reactants, the peak representing the activation energy needed to get started, and the final energy of products. The difference in energy between products and reactants is the heat of reaction. If products are lower in energy, it's exothermic, KH is negative. If products are higher, it's endothermic, KH is positive. A catalyst just lowers that activation energy peak, making the hill easier to climb.
So reactions proceed until they reach equilibrium. What does that actually mean?
Equilibrium is a dynamic state. It doesn't mean the reaction stops. It means the rate of the forward reaction, reactants, products, becomes exactly equal to the rate of the reverse reaction, products, reactants. Because the rates are equal, the net concentrations of reactants and products remain constant. It looks like nothing is happening, but both reactions are still going at the same speed. A solution at equilibrium with undissolved solute must be saturated.
And if we disturb an equilibrium, Le Chatelier's principle helps us predict what happens.
Yes, Le Chatelier's principle is brilliant. It says if you apply a stress to a system at equilibrium, like changing temperature, pressure, or concentration of something, the system will shift in a way that relieves that stress. So if you add more reactant, the equilibrium shifts to the right to consume it. If you increase pressure on a gas reaction, it shifts towards the side with fewer moles of gas. Important note, adding a catalyst does not shift the equilibrium position, it just gets you there faster.
This ties into broader tendencies in nature regarding enthalpy and entropy.
It does. Enthalpy, related to heat, and entropy, related to disorder or randomness, are key thermodynamic concepts. Entropy is basically a measure of disorder. Gases have high entropy, solids have low entropy. Nature tends to favor processes that increase entropy, get messier, and decrease enthalpy, release energy, become more stable. Spontaneous reactions often move in these directions.
Okay, let's explore the world of charged particles and redox reactions. I remember Leo says G or E, or oil rig.
Those are the classic mnemonics.
Yeah.
Leo says GER. Loss of electrons is oxidation, gain of electrons is reduction. Oil rig, oxidation is loss, reduction is gain. The key idea is that redox reactions involve the transfer of electrons. One substance gets oxidized, loses electrons, and another gets reduced, gains electron. They always happen together. If sodium reacts with chlorine, sodium is oxidized, loses E, chlorine is reduced, gains E.
And we track this using oxidation numbers.
Exactly. Assigning oxidation numbers helps us see which element gained or lost electrons. Remember, an uncombined element always has an oxidation number of 0.
And redox reactions are the basis for electrochemical cells. Two types, voltaic and electrolytic.
Right. Voltaic cells, also called galvanic cells, are spontaneous redox reactions that generate electricity. Think batteries. Chemical energy is converted to electrical energy. Oxidation happens at the anode, reduction at the cathode. Electrons flow from anode to cathode through an external wire. A salt bridge allows ions to flow and maintain neutrality. Electrolytic cells are the opposite. They use electrical energy from an outside source, like a battery, to force a non-spontaneous redox reaction to occur, used for electroplating or electrolysis. Electrical energy is converted to chemical energy. Still, oxidation at the anode, reduction at the cathode, electrons flow anode to cathode, but it's driven by the power supply.
And what happens to the electrodes themselves? Does their mass change?
Generally, yes. In both cell types, the cathode where reduction occurs often gains mass as metal ions from the solution plate onto it as solid metal. The anode, oxidation occurs, often loses mass as the metal atoms turn into ions and dissolve into the solution.
Okay, let's shift to acids, bases, and salts. What are their basic properties?
Acids typically taste sour, conduct electricity in solution, react with bases, neutralization, turn litmus paper red, and phenolphthalein colorless. Bases usually taste bitter, feel slippery, conduct electricity, react with acids, turn litmus blue, and phenolphthalein pink.
And there are two main definitions, Arrhenius and Bronsted-Lowry.
Yes, Arrhenius is the classic definition. Acids produce H+ ions, or more accurately, hydronium ions, H3O+, in water. Bases produce hydroxide ions in water. The more H3O+ ions, the stronger the acid. The more OH, the stronger the base. Bronsted-Lowry is broader. An acid is a proton H+ donor. A base is a proton H+ acceptor. This definition works even outside of water.
And these all relate to electrolytes.
Absolutely. Acids, bases, and salts are all electrolytes because they dissociate or ionize in water to produce mobile ions, which allow the solution to conduct electricity.
What happens when acids react with metals?
Acids react with metals that are more active than hydrogen, check table J, to produce hydrogen, gas, and salt. So zinc reacts with HCl, but copper won't.
And the reaction between an acid and a base is neutralization. What does that produce?
Neutralization produces water and a salt. The H+ from the acid combines with the OH from the base to form H2O. The remaining ions form the salt.
What?
And this leads to titration, right, for finding unknown concentrations.
Exactly. Titration is how we figure that out. You carefully add a solution of known concentration, the titrant usually from a Buret, to a solution of unknown concentration until the reaction is complete, usually signaled by an indicator changing color. Then you use the titration formula, M acid, V acid, M base, V base, sometimes adjusting for the mole ratio to calculate the unknown molarity.
Precisely.
So how do we measure acidity or basicity? Simply the pH scale.
The pH scale is the common way. It's based on the concentration of hydronium ions H3O+. If H3O+ is greater than OH, it's acidic, pH 7. If H3O+ is less than OH, it's basic, pH 7. If they're equal, it's neutral, pH equals a 7.
And it's a logarithmic scale, right? So pH 4 is much more acidic than pH 6.
Huge difference. Yes, it's logarithmic base 10. Each whole pH unit represents a 10-fold change in H3O plus feel. So pH 4 is 100 times more acidic than pH 6. As the H plus concentration goes down, the pH goes up. We also use indicators like litmus or phenolphthalein that change color in specific pH ranges.
All right, let's venture into organic chemistry, the chemistry of carbon. What's so special about carbon?
Carbon is unique. It can form 4 strong covalent bonds and bond to itself to form long chains, branch chains, rings, and complex networks. This incredible versatility allows for the vast number and variety of organic compounds essential for life.
The simplest are hydrocarbons, just hydrogen and carbon, saturated versus unsaturated.
Right. Hydrocarbons containing only single carbon bonds are saturated, like alkones. If they contain one or more double or triple carbon bonds, they are unsaturated, like alkenes and alkynes. We group them into these homologous series based on their bonding and general formulas.
And isomers, same formula, different structure.
Exactly. Isomers have the same molecular formula, but different arrangements of atoms, leading to different structures and properties. We also identify organic compounds by their functional groups, specific arrangements of atoms like LOH for alcohols or DeoxyOH for carboxylic acids, which determine their chemical behavior. Reference tables help identify these.
Organic compounds also have characteristic reactions.
Yes, things like addition reactions, adding across double triple bonds, substitution reactions, swapping atoms, and esterification, forming esters, often fragrant compounds.
Finally, let's touch on nuclear chemistry changes inside the nucleus itself. Very different from chemical reactions.
Fundamentally different. Nuclear chemistry involves changes to the protons and neutrons in the nucleus. A key process is transmutation, where one element actually changes into another element because its nucleus changes. This can be natural, radioactive decay, or artificial induced, like fission or fusion. Chemical reactions only involve electron rearrangements.
And nuclear stability depends on the proton-to-neutron ratio.
Yes, there's a zone of stability. Nuclei outside this zone are unstable, radioactive. Many heavy elements, especially artificial ones, have no stable isotopes at all.
This leads to different types of radiation being emitted: alpha, beta, gamma.
Right. Alpha particles are like helium nuclei, mass 4, charge +2, low penetration. Beta particles are fast electrons, mass 0, charge -1, moderate penetration. Gamma rays are high-energy photons, mass 0, charge 0, high penetration.
And their charges affect how they move in an electric field?
Correct. Positive alphas bend towards the negative plate, negative betas bend towards the positive plate, and neutral gammas go straight through. Importantly, in all nuclear reactions, both mass number and charge must be conserved on both sides of the equation.
Nuclear reactions like fission and fusion release enormous amounts of energy compared to chemical reactions. Why?
Fission is splitting a heavy nucleus, like uranium, into lighter ones. Fusion is combining very light nuclei, like hydrogen isotopes, into a heavier one. Both release immense energy because a tiny amount of mass is converted directly into energy, according to E.C.Apar. Even a small mass, multiplied by the speed of light squared, yields a huge energy. Fusion requires incredibly high temperatures and pressures to start.
And the concept of half-life is central here. What is it?
Half-life is the time it takes for half of the radioactive nuclei in a sample to undergo decay. It's a constant characteristic for each specific isotope, ranging from fractions of a second to billions of years.
And it's incredibly useful, right, for dating, medicine?
Hugely useful. Carbon-14 dating for organic remains, iron-131 for thyroid imaging and treatment, cobalt-60 for cancer therapy and sterilizing food equipment, technetium-99 for medical imaging like brain scans, uranium-238 for dating rocks.
But there are also significant risks with radioactivity.
Absolutely. The big concerns are managing long-lived radioactive waste safely. The biological damage radiation can cause to cells, leading to health issues like cancer, and the potential risks associated with controlling nuclear reactions, like reactor safety.
Wow, what a journey. From the simplest models of the atom wrestling with protons and electrons, all the way to the immense power locked inside the nucleus, we've really covered the core of fundamental chemistry.
We really have. From Dalton's initial ideas through bonding, reactions, states of matter, the periodic table's elegance, solutions kinetics, and finally, nuclear changes. It shows how understanding these building blocks lets us classify, predict, calculate, and even harness energy.
So the big takeaway for you listening right now, hopefully you've got a solid mental map of these key chemistry concepts. The connections between them, the core principles, this should be a great shortcut to feeling really well informed about how the physical world works at its most basic level.
Yeah, and thinking about all this, especially nuclear stability, it makes you wonder, Given this incredibly complex balance of forces within the nucleus, how might our deepening understanding actually allow us to maybe design and create entirely new, stable elements someday? Elements beyond what's even on our current periodic table? And what completely unforeseen properties might they possess?
That is definitely something to think about. A whole new frontier. We hope this deep dive has fueled your curiosity and given you a strong foundation. Until next time, keep digging into the knowledge.